Well, hello friends. Welcome back to emulator hacking. Today we are going to work on emulator performance a bit because it is now possible to run the browser in the user space emulator thanks to a bunch of support for floating point math added by Nico and some work done by myself. But as you can see here, it is extremely slow. So it's not really realistic to use it for any kind of active testing just yet. So we're going to need to do a bunch of performance analysis and improvements. So I figured we could just get started on that. So of course we'll start by grabbing a profile and maybe just turning this thing off here so we can look at our profile in peace. Okay, so right away we can see that 96% of time is spent in Malloc Tracer find Mallocation. So this is called every time that we have to audit a read or write operation. Essentially anytime that the emulated CPU reads from memory or writes to memory, we search through our set of known malloc allocations to figure out, like, are we tracking this address? And that's how we are able to figure out, like, is this within the bounds of a malloc allocation or outside the bounds? So basically the user space emulator is doing mostly this. So we're gonna have to do less of that. So let's take a look at how this is currently implemented. So we have this thing called a Malloc Tracer, and this thing is notified whenever there is a malloc or free or realloc event that happens in the emulated program, and then it sort of builds up its own picture of the malloc heap. And whenever there's a memory access in the CPU, it calls audit read or audit write, and this is what might end up causing us to log an out-of-bounds access complaint, for example. So here is this thing we call a mallocation. A mallocation is just how we represent a malloc allocation internally in the emulator. So it has an address, a size, whether it's freed or not, and then we also keep a backtrace for the allocation event and a backtrace for the free event, so that if you access a piece of malloc memory after it's been freed, we can actually tell you this is used after free, and it was freed with this backtrace. So there's quite a bit of information per mallocation. Now the way we store the mallocations is like this. So this is definitely why it's so slow. We just keep them all in a vector, and whenever you want to audit an access, then we call find mallocation. As you can see, this is the dominant function here in the profile. And find mallocation is a sad, long walk across all of the mallocations, and we're checking if the mallocation contains the address. So essentially, we're walking an unsorted list of mallocations to figure out, to look for, like, the one we want. Very, very not gonna perform very well. So my thinking here is that we want to have a much more efficient data structure so that we don't have to walk this whole thing. But it would be cool instead if we could have a constant time lookup somehow. And we will want to take advantage of the fact that we're using our own malloc implementation, so this doesn't have to be generic, right? Like, we can exploit the fact that we control malloc, or we control the memory layout of malloc. So I think what we want to do is we want to keep track of some higher order malloc metadata, or like, we want to keep track of more malloc metadata in the emulator itself, so that we would know which malloc block we're looking into. Because the way malloc is implemented in the libc is that we have these things called blocks, and there are two types of blocks. There are big allocation blocks and chunked blocks. And a big allocation block is like a large, I think it's, if it's like more than 32 kilobytes or something like that, Then we make a single big allocation block, which is an M-mapped block. But for smaller allocations, we allocate 64 kilobytes and then split it into chunks so that we don't have to keep calling mmap every time. So both big allocation block and chunk block start with a common header. So this is what we'll find at the start of any mallocation. So for chunk block, this is pretty simple. For big allocation block, it's a bit messier, and the reason is that with chunk block, we always allocate these 64 kilobytes at a time, and we ask for 64 kilobyte alignment as well. So os alloc. Yes, we're passing the block size here as the alignment, which means that for any address within a chunk block, we can mask it, like we mask off the bottom bits, and we get the address of the chunk block. So that's really good. But for a big allocation block, it may be larger than 64 kilobytes, right? So if you have an address that's at the tail end of a big allocation block, and you mask off the bottom bits, then you're not going to end up at the big allocation block header. You're going to potentially end up in a subsequent 64 kilobyte allocation. Anyway, I think if we just make this fast for chunk blocks right now, that would already be a huge improvement. So what I'm thinking is we'll make the emulator aware of chunk blocks, because then we can figure out the mallocation way faster, because then we just have to look up the chunk block address in a hash table of chunk blocks that we keep track of. Anyway, let's see how we'll do that. So in Malloc Tracer, we'll want to have some idea of chunk blocks. Chunk block, Malloc, I would call it like a Malloc chunk block maybe. And so we'll have the address, and we'll want to keep track of the chunk size. And maybe that's good enough. And then, of course, we want to have our list of mallocations in there. So maybe just to start with, we can do this. But then we can turn these into... Oh, wait. We'll see what we do with this. Because I guess a chunk block will have a finite number of mallocations, actually, depending on the chunk size. Yeah, okay, this is gonna be good. Mallocation chunk block. I don't know what to call this exactly. I don't want to call it chunk block because it's too close to the real name of it. At the same time, we're within the Malloc Tracer class here, so maybe that's okay. Tracked chunk block. Let's call it that. Okay. So then we'll have a hash map of flat pointer to a tracked chunk block. Okay. Yeah, I think this is going to be good. So let's see. For the big allocations, maybe we can keep these on side here, like big mallocations. So if something doesn't fit in a chunk block allocation, we'll put it in this guy. That'll be okay. Okay, and then find mallocation. First thing it has to do is check for if we have a chunk block for this address. So that would be possible chunked block is address and the chunked block mask, which that's 64 kilobytes minus 1. Is that what we want? I guess. Okay, so if auto chunked block is chunked blocks get what would we get here? Chunked block has value. Okay, this is how we do it. Then we'll iterate his mallocations, otherwise we'll iterate our own. So we're not going to keep this linear scan forever. This is just something we're doing right now. Chunked block value. Okay. And find mallocation before. So these are for reporting errors. Want to find the mallocation before a given address and the one after a given address. I think maybe it's okay that these are not optimized right now because they're just for error reporting. So I'm going to go ahead and make kind of slow versions of those. For each mallocation. Okay, and then here we can just call for each mallocation. Something like that. Okay. All right, and then when we perform a malloc, so let's be a little bit lazy right now. So we know that the largest size class in malloc is 32752. So I'm just going to be a little bit lazy here, and this is something we have to clean up later, but if size is less than or equal to this, then it's a chunk block allocation, otherwise it's a big mallocation. So Let me clean this up of hard coding the chunk size Malloc uses. Right. So, existing retract chunk block is get address and chunk block mask. I need to put that somewhere better. Maybe here. Okay, like this, and block size like that. Okay, so if track chunk block has no value, then m chunk blocks set. Wait, let's compute this first. The chunk block address. Okay. So there's a double hash lookup here. It's kind of ugly, but that's not perfect. Whatever. I'll put another fix me. Okay, so now we have a tracked chunk block. So we can set its, actually we only need to do this when we build a new one. The address will be chunk block address. And the chunk size will be, I guess we actually don't know the chunk size if we don't read that piece of memory. So we can read from it. And the, wait, where is that stored? Chunk size, bytes per chunk is an M size. Okay, so it's the second word, second size T in the common header. So 32 bits into it. So read from 4. Value. Okay. Tracking chunked block at, let's see, with a chunk size this. All right. And then we'll just append this guy here. I think later we're going to set it at a fixed offset into the mallocations vector, so so that we can index right into it instead of having to scan. But right now we'll just append index directly to the correct spot in the tracked chunked block mallocation list instead of append. Yeah. Okay, and then when you freeze something, we have to work out the same thing. So actually we don't know what size it is. So all we have to do when we free here is we have to work out I guess what we can do is mallocation is find mallocation address. I don't know why this was written that way. That's kind of weird. Because when we free a mallocation, we don't actually throw away any of the information about that mallocation. We just update the state to freed, and we log a backtrace so that we can look it up later. We don't actually forget the mallocation. All right, and then is reachable. So this is for leak detection. We don't have to optimize this right now, so we're just going to use for each mallocation again. Okay, I think we'll have to use decisions here though. So return true. Right, so true, return, iteration, decision, break. And then we're basically good, except this guy needs to handle decisions, so. Oops. Const, I guess. Yep. And for the leak report, we'll do the same for each mallocation. You don't like a lot of things, apparently. Probably this guy right here. And who has an incomplete type? It is tracked trunk block entry. Malloc Tracer. Okay, wait. And then we are assigning to a read-only object. Why is that? Well, okay. returning here? Oh, it's const. Okay, so we'll just const cast, whatever. Oh. This is, right, I'm not doing this right. I need to lock the mallocations in the trunk block here. Okay. So we're getting closer. Another const cast that we need here somewhere. Here. 162. Yes. And 175. Okay, so this is definitely not going to work, but just to get some idea of where we are, because I got a little disoriented here. Okay, so it's starting to track chunk blocks, although the addresses are totally bogus. And we're seeing a lot of buffer overflows being reported. So let's see, tracking chunk block. And of course I want to, I'm masking incorrectly. I'm stupid about that. Where's the block mask? I have to tilde that thing so that we flip the bits. Otherwise we're just only looking at the bottom bits, the ones that we want to mask off. Okay. Alright, so we're up and going here. Now we're getting a lot of complaints coming in. What is this about? Conditional depends on uninitialized data. Yeah, so there are issues in the emulator right now that it's way too eager to say that something is depending on uninitialized data. So I'm just gonna early return here from that issue in particular, because the new floating point instructions, they're not being careful to preserve the tracking of uninitialized data state. So that's something that needs to be fixed. But it's all very fixable. We'll get there too. So let's see. Just turning off the reporting here, I feel like we should be able to. Ooh, look at that. That got going pretty fast actually. And we crashed, but it's a separate issue. Still, this is definitely a lot faster than before. So before I started working on this today, this thing said like this page loaded in 34 seconds or something like that. I think it did. Actually, I tweeted it out, so let me see what it said in the screenshot. Yeah, so 34 seconds previously, and we're, oops, dang it. We're down to 2 point something seconds, which is amazing. Very cool. So let's profile this thing though. And the leak report looks kind of reasonable. I think what we're seeing here is what is this? Are we leaking something in main? I think that's going to be an operator new bracket screwing up somehow, but I'm not sure. Do we have that? Because I know that we're not taking care to track those correctly. Browser main. Well, yeah, that's not gonna work. Anyways, let's ignore that for now, and let's just get a profile of this thing running instead. So we have to actually hurry up here. All right. So find mallocation still up quite high, but already like significantly faster, as you can see, right? Because now we don't have to sift through every single mallocation, but instead we sort of we first find a chunk block, and then we only have to look through the mallocations in that chunk block. Now we can do this, we can still do a lot better than this, but this is already a huge improvement. So now we're looking at find region showing up near the top as well. So find region is another data structure traversal that's also, look here, it's a crappy vector traversal. Now that find mallocation is sort of stepping back a little bit, then other stupid data structures in the emulator move to the front, and you can see that here this is memory region traversal. So, or memory region lookup. A region is like when you call mmap, then what you get back is a region of memory, right? So we're looking for the corresponding memory region so that we can do permission checking and stuff like that. So I think we'll ignore that one today and focus on the mallocations and try to get what we can from that. But this is already very, very positive here. And yeah, like the fact that the leak report, when you exit the program, the fact that that's a bit slow, we can live with that for now. Like obviously it would be nice to make it faster, but right now we just want the runtime to be faster. So, so once we know the chunk size, then we can figure out the number of total chunks in this block. Chunk count. So I think what we'll do is we'll compute that here. After we initialize the chunk size, so we'll do something like this. Maybe even just block, yeah. Chunk count. This code is not very defensive. We're just assuming that you're using rmalloc. So, but I think that's okay. Like even later, once we have dynamic libraries, I think what we'll do is we will, when you run in user space emulator, we will sort of load our own malloc, like the user space emulator's own malloc, and then we could do even more interaction between malloc and UE. But even now, like just exploiting the fact that we know how the data is laid out in the malloc heap is tremendously useful. So the chunk count is the block size divided by the block chunk size. Sort of. we have to subtract the size of the header. Chunked block. So it's 24 bytes. Again, we're gonna be a little ugly here and hard code it. Fix me, don't hard code. Subtracting size of a malloc chunk block. So a nice way to clean this up maybe would be to like make a malloc.h or malloc internals.h header that we could pull in here, and then we would see all these things as constants. But right now we're just trying to make something that works. Okay. So, oops, chunk count is this. Block address, block chunk size, block chunk count. And what we'll do with the chunk count, of course, is that we'll take the mallocations and resize it to the block chunk count. So, now, we have a whole bunch of these. So when we append one of these boys, sized used. So here we'll say true, or rather here it's true. So now what we want to do is, like I was saying here, like index directly to the correct spot in the mallocations vector, because now we know that it should accommodate this. So we need to compute the chunk index of the chunk we're looking at. So that would be chunk offset is address minus block address, and then the chunk index is the chunk offset divided by the block chunk size. And then I think we can just do block mallocations chunk index equals this. No append. That's very interesting. Okay. And then when we do a find mallocation, we shouldn't need to walk the whole, we shouldn't need to walk the mallocations here, but instead we compute the offset. And the chunk index. And then the mallocation is the block mallocations at chunk index. And all we need to check here is mallocation used. So used just means that we've ever put something there. It will never become false once it's become true. So it's like, it only goes from false to true. Once you free a block, it will be freed, but it will still be used. In this data structure, at least. All right. So what am I forgetting about here? I guess now when we walk all the mallocations, and for each mallocation we want to skip over the unused ones. So if mallocation used, and call back mallocation. Yeah. Exactly. So we have to skip over the unused ones. But outside of that, I think we're good. Yeah. Okay, let's see how this goes. Oh, well, this was not popular. Oops. All right, so what did we mess up then? The chunk count, audit read. So when we do a fine mallocation, this is failing now. So we have the correct block, presumably, but here we can assert that the mallocation contains the address, because it always should now. I think maybe that would cause us to fail right away. We can at least see that that's what's happening. Getting rid of scans is like the name of the game here. We have to get rid of all the linear scans that we can. So yeah, we're failing here after a whole bunch of complaints. All right, all right, all right, all right. Oh, wait, shit. I'm doing the address computation wrong because I'm forgetting about the 24 bytes of header. Address minus block address plus 24. Yep, here comes that header. That's the size of the chunk block data structure header for the header data structure. So our chunk index is probably wrong. And yeah, there we go. 1.5 seconds, down from 2.7, down from 34. Very respectable improvement. Really kick-ass. Of course, we're crashing on hover, but that's because we have some unimplemented floating point support that we need to get to, but this is pretty kick-ass. Oh, I wonder if we can run the breakout game. Nope, not yet. There are a lot of things that need some help to run still, but you can see that we're clearly improving, which is pretty cool. So let's see if we can get a profile of this user space emulator. Okay. Oh. Oh, I see. So now we get to see stuff going on like during program start while it's loading the debug symbols for the for binary. We're doing a sort here of some type. Very painful. We're sorting a set of strings, and it's just spending so much time in compare exchange. That's not very nice. I guess because of the thread safe ref counting and string. Yeah, so we could probably improve that. But once we're in this function here, so let's just ignore the stuff at the start. Can we go here instead? Yeah, so profiler filtering is really nice. Like if I don't care about startup time, how much this is, it's about first second or so of execution. But once we're here, we filter, go to top, and find region dominates. And then we have read 32. So like memory reads obviously dominate. Find mallocation down here, pretty good. Update code cache. Oh, maybe that could be made faster, actually. And we have some goofy lag in the mouse cursor. I don't know what that's about, but it's unrelated to these changes. Anyway, find mallocation. Very cool. So this makes me wonder, like, would it be possible to scroll here? If I can just get the cursor here. Ah, nope. Unimplemented instruction. Okay, all right. How about a resize though? I gotta try a resize. Oh, come on, man. Let me resize. Probably just need to implement a couple more instructions. But it would be so cool if we could resize. It works. Dude. Very, very cool. Okay. So, this is quite, some of this is quite ugly, actually. I don't love that. So let's see if we can make some things a little bit nicer. So chunked blocks, for example, could store non-null on pointers because we never want to have null thing in here. It doesn't change a whole lot, it just codifies the fact that we don't track null blocks. And, you know, maybe we'll make that malloc internals header thingy. Libc. Oh, we have malloc defs.h. What is in there? You know what? Why don't we just do it in here? So let's see, chunked block, or who uses this? Malloc defs is used by CPU code in the kernel. Okay, so I think we can probably put this in there. Chunked block. Inline linked list. Okay. It's a little bit arbitrary to put this in malloc-defs.h, but at the same time, it's just an internal header anyway. So I think that's going to be okay. And then here we can just pull that in. So malloc-defs. And we don't have to say 24 anymore. We can actually say chunked block. this stuff should probably move into chunk block. Yeah. Oh man, it's gonna be excellent. So that would be offset of chunked block M size. There we go. And okay, all right. Chunk count. Do we actually need chunk count at this point? Chunk count? We only use it up here, so we don't need to store that. Yeah, it's all good. And oh, dang it, I messed that up. This block size. Okay, slightly crappy search and replace job, but we got it done. And then we also need the final size class here. I think maybe we can just move that to Malloc defs from now. Okay, maybe this is going to be good. So Malloc defs just got real beefed up because, also I don't know what that one's about. I think it's already has a lock and everything. I don't know why that's still there. I'm just gonna yoink it. Or wait, no. This is not good engineering. I shouldn't do this. I'll leave that for later. But I feel like this is turning out pretty good. So now you can just pull in malloc-defs.h and you get to see all the data structures used by malloc. And we wanted to, instead of hard coding 32752 here, we want to pull in size classes, num size classes -1. I think, oops. Wait, the last one is 0. So shouldn't this be -1? That's weird. Then maybe we should namespace these things. I don't know. Don't have to do everything right in this particular patch. I think it's already going to a good place here. All right. That's great. Very cool. Can we maybe make it go to another website? Let's see. Takes a little while to exit, that's true. Yeah, we can improve that later. This is the leak report. Should probably look into these. Anyway, there will be plenty of time for that, so I just want to see if this can load another website. Okay, well, we crashed in some floating point math instruction, presumably. So, whatever, still good. I'm still happy with the outcome today, so I think we're good to commit here. First off, we'll do the libc changes. So see, move Malloc's sum of Malloc's data structures into malloc dev.h. This allows UE to see what the heap metadata looks like. Yeah, that's helpful. And then yeah, we have a double hash lookup that's kind of ugly, but I'm just going to leave that in. So room for improvement. There's plenty of room for improvement here, actually. Like the big mallocations are still using a linear scan, but just fixing up the chunked allocations, as you can see, was hugely helpful. And I'm sure that this can be expressed in a more terse and concise way. We can probably do some helpers for various things, but I'm happy with this for a first cut. So all of those changes, not that changed yet. Make Malloc auditing significantly faster. Actually, this is what we'll write here. We'll say track malloc chunked blocks for faster auditing. Instead of doing an O of n scan over all the mallocations whenever we're looking up whenever we're doing a read-write audit, UE now keeps track of chunked blocks and uses keeps and their chunks. This allows us to chunk block lookups are all one. Both the block lookup and the chunk is O1. Okay. Note that the old linear scan is still used for big allocations, but The vast majority of mallocations are chunked, so it's a huge help. This helps a lot. All right. UE knows what chunked blocks look like by including malloc.h from libc. Yeah. There are probably ways that this can be improved greatly. They're just not popping out to me right now, but we'll probably think of them soon enough. Maybe we should make a helper for this thing right here, like the chunk index can be block chunk index of chunk index from address for address. So how would that look like? It would be tracked chunk block. Address and then this address. Something like that. Is that better? I feel like that's maybe a little bit better. Then we could even do mallocation for address. So let's see what that would do. It would be like chunk index for address, like that, right? And then block allocation for address. I don't know, like, is this better? Maybe it's a little bit better. Maybe. Let's see, and then where else did we do this? Size of chunk block. So this would be compressed into block mallocation for address. That's a little weird, but maybe it's okay. The chunk count is simply the block mallocation's size at that point. Yeah, all right. It's a little bit tidier. I didn't do that right. There we go. Okay, I guess maybe we can get rid of that double hash lookup too, since we're tidying things up. Add some helpers to tidy up track chunk block. Yeah. And then the double hash lookup here is basically first we check if we already track this block, and if we don't, then we have to insert a new one. So do we have ensure of some type? We have ensure. That's not really what we want right now. So let's do it this way. So chunked, tracked, chunk block. So if we don't find it, then we'll create it. Oops. And here we'll do block is new block putter, and we'll move block into the map. Else, if it was in the map, then block is tracked chunk block dot value. Like that. Oh wait, it's a const one. Okay, so tracked chunked block. Cool. And then we already have the block at that point. Yes. Excellent. So now we don't have the double hash lookup either. Not that a double hash lookup is particularly heavy, but it still feels nice not to do it. Double hash lookup avoid one hash lookup in targeted malloc. Yeah, that's okay. That's a decent patch. It's very spacious here. Okay, I think that's pretty good. So I think I'm gonna be happy here for today. Obviously, we've been able to make a huge improvement, and let's run something else. Just see that it works. Text editor. Hello from text editor. very cool. It is very neat to be able to run GUI apps. And here we crash because of a missing syscall in the emulator. So obviously there's still a lot of work to do, but we're moving forward. So yeah, this will be the end of today's video. So I hope that you saw something interesting here, and thank you very much for stopping by and hanging out. I think this was a particularly rewarding session because we basically made the browser at least launch really fast, and there's clearly room for more improvement here, but I think just being able to run the browser in the emulator is going to be absolutely huge for debugging, and there's all kinds of interesting things we can do to interact between the emulator and the JavaScript engine, for example, make it aware of garbage collected objects and stuff like that. So a lot of stuff to look forward to. Anyway, this is it for today, so thank you very much for hanging out, and I will see you next time. Bye.